Don't drink too much. Don't drink too much.
Okay, I think we will get our proceedings underway this morning. Welcome back to day 2 of our sesquicentennial celebration of the Academy, examining the Academy's history over the last 150 years. Today we're going to examine the nation's infrastructure, health, information, and education. And as I think Dan and Ruth mentioned yesterday, that one of the things that has really struck us as we started our archival research here is that the public knows a lot about the Academy's work on doing studies on some of these controversial issues, climate change and other things. But what they don't often know about is some of the stuff that's a little lower profile, which contributes to really a lot of the stuff in our daily lives. The food we eat, the roads we drive on, what our children learn in schools, the way we are treated when we go to the doctor. And today's panels are going to look at some of what we think of as the nation's infrastructure and the Academy's contributions to that. Our first panel looks at some of this work on radiation hazards and radiation standards, although this is not entirely without controversy either. But we have a distinguished panel here this morning, and we will start with Angela Creager to give our main talk. Angela is the Philip and Beulah Rollins Professor of History at Princeton University, where she specializes in the history of 20th century biomedical research. She's the author of the masterful and just published Life Atomic, A History of Radioisotopes in Science and Medicine. I highly recommend it. She's recently begun a new project on science and regulation in the 1960s through the 1980s, focusing attention on how researchers conceptualized and developed techniques for detecting environmental carcinogens. So it is a great pleasure to welcome Angela to the podium.
Well, let me just thank the organizers of this symposium. It's really terrific to have an opportunity to reflect on the contributions of the National Academy of Sciences to American life generally. My charge today is to talk about what role the National Academy of Sciences played in research and policies around radiation hazards. And while working on this topic, when I was doing work on my book, the history of radiological risk and protection presented an enigma to me. Specifically, why was it that not until the fallout debates did the U.S. government, and indeed many scientists, begin to take seriously the hazards of low-level radiation, although many geneticists had been warning of them for decades? After all, H.J. Muller had demonstrated in 1927 that X-rays could induce mutations, and this finding was rapidly extended to other forms of radiation. Radiation had also been correlated with the appearance of cancer, especially leukemia, from the 1920s and 1930s, most tragically in the young women who were radium dial painters. However, these two observations were rarely linked, as scientists and safety officials usually treated genetic effects, mutations, as distinct from somatic ones. The elevated risk of cancer was considered a somatic effect of radiation, as opposed to its genetic effects, principally mutations. So then somatic effects could directly affect the health of the individual. Genetic effects were thought to affect only one's offspring. So today I want to explain how the science on these two consequences of radiation converged and what role the National Academy of Sciences played in that convergence. Now, this separation had a long history. In the 1920s, radiation safety guidelines were set by private official bodies, such as the International Commission on X-ray and Radiation Protection, or in the United States, the National Council on Radiation Protection. And these advisory bodies tended to focus exclusively on somatic effects of radiation, which they sought to control through what was called a tolerance dose for visually detectable damage. Now, at the end of World War II, this terminology was changed to permissible dose, an acknowledgement that even the tolerance dose might not be certifiably harmless. Nonetheless, there was this threshold mentality about safety that below a certain level, hazards were essentially negligible. At the end of World War II, the American government was surprisingly unprepared for the devastating effects of radiation due to its atomic weapons in Japan. The military expected, as Norman Ramsey has said, that any person with radiation damage would have been killed with a brick first. So the distinctive and disturbing effects of atomic weaponry were documented by the military's Joint Commission for Investigations of the Effects of the Atomic Bomb in Japan, and subsequently by the Atomic Bomb Casualty Commission, which has been studied extensively by Susan Lindee. Now, the National Academy of Science oversaw the Atomic Bomb Casualty Commission, or ABCC, which became and remains the most important source about data on the long-term effects of radiation in humans. But the American government did not widely disseminate this information, to be sure, and Japanese accounts were censored, although some journalists did document the suffering of the peculiar suffering of Japanese survivors in the American press. But it was not only a question of the suppression of information. Atomic energy had already developed a different, more positive image. While the dangers of radiation had been documented since the earliest days with X-rays and radium, so had the power of radiation to treat disease, especially cancer. Post-war optimism about the medical uses of radioisotopes and neutron sources drew on decades of efforts to harness the therapeutic promise of radioactivity, beginning with the Curies. In the 1930s, cyclotrons supplied a growing demand for artificial radioisotopes, especially phosphorus-32 and iodine-131, both of which were used clinically. Reactors developed for the bomb project could produce radioactive materials on an industrial scale. After Americans achieved victory against the Axis powers, many proclaimed that atomic energy would win the war against cancer. And I just want to draw your attention to this really striking cartoon in the op-eds of the Dallas Morning News. This is just a few days after the bombing of Hiroshima and Nagasaki, and already there's this picture of atomic energy next being used to destroy, cancer. On May 15th, 1947, during budget hearings, Representative Everett M. Dirksen argued that the Atomic Energy Commission should have a $25 million cancer program. Cancer killed one person every 3 minutes, as he asserted. This amounted to 72 Pearl Harbors every year. It seemed especially fitting to Dirksen that the successor to the Manhattan Project should take on the cancer problem. As he said, if we are going to spend a few $100 million in the atomic energy field to perfect an instrumentality of death, then let us take a little of that money to develop an instrumentality to preserve life. Now, one of the main programs that the AEC mounted to fight cancer was the production and distribution of radioisotopes. And I've written extensively about this. The initial plan for it was hatched by scientists within the Manhattan Project as a way to try to free the atom from military control. And it was the Manhattan Project that announced it in the summer of 1946. And over the next several years, a full-fledged radioisotope production and chemical facility was built up at Oak Ridge National Laboratory. Here you can see the reactor that was used for this purpose. And on this slide, you can see the production and shipping facility that was built right alongside the reactor at Oak Ridge. And the government highly subsidized radioisotopes that were then being used by scientists and clinicians. So the supply of accessible and inexpensive radioisotopes transformed fields as diverse as molecular biology, ecosystems ecology, and nuclear medicine. Popular coverage of the AEC's venture presented radioisotopes as magic bullets that would cure diseases, especially cancer. And this really striking image is from a story that ran in Collier's magazine in a whole section on atomic energy. And the story called Medical Dividend began with the quote, "The first benign results of atomic bomb research have been new tools for medical scientists which promise cures for hitherto incurable diseases," which was basically a code word for cancer. This was the public face of radioactivity immediately after World War II, even though that healing mushroom cloud never did quite pan out. David Bradley blamed this mentality for the blasé attitude about radioactive contamination following the 1946 test explosions in the Pacific. As he wrote in No Place to Hide, "We were surprised at first to find so little interest in the bikini tests, but we really had no right to be. Atomic energy was an uncomfortable subject. Things like John Hersey's Hiroshima were rough. How much more pleasant to consider the coming miracles of healing, the prolongation of life, the days of sunny leisure which people were everywhere promising." Now, some did voice concern about the dangerous effects of radiation. So, for example, in 1947, Paul Henshaw, who was an officer in the occupation forces in Japan and a biophysicist who went on to work for the AEC, wrote this popular article, Atomic Energy, Cancer Cure or Cancer Cause? Strikingly, however, his main concern about cancer was that the burns in Japanese survivors might turn malignant. This was based on kind of an inflammation view of the cause of cancer. And he had a related concern that cell damage resulting from high-energy radiation could also cause cancer. But in his view, low-energy radiation was entirely off the hook. As the article concluded, we know now that exposures less than 1 Rontgen a day are safe. Now, many geneticists dissented from this sunny view of the risks of low-level radiation exposure from the AEC's vast program of weapons testing and civilian development, and eventually they were heard. But physicians and health physicists tended to hold the key government positions and articulate its policy, which rested on the assumption that there was a safe threshold for radiation exposure. Now, the genetic effects of radiation were addressed in 1949 by Robley Evans, a physicist known for his studies of radium dial painters. In this article that was published in Science, Evans gave a relatively reassuring picture of the genetic effects of radiation. He asserted that exposure at or under the government's permissible level would not significantly increase the mutation rate beyond the spontaneous level. Now, Mueller, whose public statements on this were clearly being rebutted by Evans' article, sent a long letter of criticism to Evans, or as Evans put it, a few points of scientific interest and many matters regarding personalities and prejudices. Evans, it has to be said, had a sense of humor about Mueller. I found a mimeograph of a Science Service press release about this 1949 article in the Evans papers, and it says, queried in Bloomington, Indiana, Dr. Mueller stated that he had examined Dr. Evans' manuscript before its publication and had criticized some of its assumptions and its conclusions in considerable detail, and Evans wrote in green ink, and that ain't all, sister. But it was not only Mueller who criticized Evans' calculations. Sewell Wright argued that the figure that Evans used for the spontaneous mutation rate in humans, 10 to the negative fifth, extrapolated from pathological conditions such as hemophilia, was likely 2 orders of magnitude too high. He used a lower estimate based on the spontaneous mutation rate in Drosophila and calculated that exposures within the permissible dose could in fact alter the incidence of mutations significantly, although perhaps not detectably because most mutations are recessive. Now, the military safety guidelines at this point was set according to a doubling dose on the assumption that exposures up to that causing double the spontaneous rate should be considered normal and safe. Evans' numbers gave a doubling dose of 300 Rontgens, whereas Wright's revised number lowered it 100-fold to 3 Rontgens. So personnel in atomic energy plants, if working near the permissible exposure limits, and many weren't, but if they were, might actually accumulate that dose within a few months. The AEC's own intramural research reinforced Mueller's and Wright's concerns. William and Leanne Russell's megamouse study at Oak Ridge National Laboratory suggested that the mammalian spontaneous mutation rate might be an order of magnitude lower than that for Drosophila, the number that Sewell Wright had used for the doubling dose. Evidence from 2 other, and that would make the exposure level at 0.3 Rontgens for the doubling dose, and that really would challenge the permissible dose set by the AEC as safe. Evidence from studying 2 other sources cast further doubt on the AEC's assumption that low-level radiation did not cause somatic damage. First, by 1952, the ABCC's survey of leukemia incidence among survivors in Hiroshima and Nagasaki documented a higher rate of leukemia among those individuals, and distance from the blast correlated with leukemia incidence, even those over 2,000 meters away who hadn't shown any signs of radiation sickness still showed higher rates of leukemia, higher rates than expected. Second, H.C. March investigated leukemia rates among physicians over a 20-year period and found a 9-fold higher incidence of leukemia among radiologists than the group as a whole. Now, after 1950, the pace of atomic weapons testing increased dramatically. Between World War II and 1950, there were only 5 atomic weapons tests. Between 1950 and 1952, there were 26 atomic weapons tests. In addition, this is the time at which hydrogen bombs were being developed and tested. They gave off much more radioactive fallout, and also much of the testing was being shifted to the continental U.S., to the Nevada Proving Ground. In March 1954, the AEC conducted a test of its thermonuclear weapon in the Pacific Proving Ground, and fallout from this Bravo shot ended up falling on a Japanese fishing boat, the unfortunately named Lucky Dragon. Nearly 24 fishermen suffered injuries from the radiation exposure, and one eventually died, and this was widely covered in the press, both in the US and in Japan. The American government, though, made no concessions to critics that these fishermen were suffering from radiation. Lewis Strauss, the chair of the AEC, publicly denied that fallout could be harmful to humans, animals, or crops. Challenges followed. Geneticist Alfred Sturtevant rebutted Strauss's denial of fallout risk in a presidential address for the Pacific Division of the American Association for the Advancement of Science, and his address subsequently appeared in Science magazine. In recounting the hazards of radiation exposure, Sturtevant connected mutagenicity with the so-called somatic effects. These were the two that have been kind of separated in the AEC's guidelines. As he said, there is reason to suppose that gene mutations induced in an exposed individual also constitute a hazard to that individual, especially in an increase in the possibility of malignant growth, perhaps years after exposure. In comparison to the kind of radiation injuries taken into account in setting a permissible dose for exposure, there was not a lower limit to the amount of radiation that might induce mutations. So Sturtevant then concluded there is, in fact, no clearly safe dosage. Now, in linking genetic effects to cancer, Sturtevant picked up on a suggestion that had been made along these lines by Muller in 1948. And this idea not only subverted the strong distinction between somatic and genetic effects, but it raised new concern about the carcinogenic potential of fallout products such as strontium-90 and iodine-131. If there was no threshold for genetic damage, then even low doses of ionizing radiation might induce cancer. Now, the initiation of this open debate between leading scientists and the AEC made for great media coverage, and this, in turn, fueled public alarm. Responding to the mounting concern, the National Academy of Sciences appointed a committee to address the biological effects of atomic radiation. Its work was actually supported by the Rockefeller Foundation. There were 6 subcommittees that were part of this committee. They were focused on genetics, pathology, agriculture and food supply, meteorology, oceanography and fisheries, and radioactive waste disposal. The 1956 publication, the first Bear Report, as it's called, included reports from each of these committees, but the media really honed in on the report from the genetics panel. And you can see this report from the New York Times. Scientists term radiation a peril to the future of mankind, and it begins a committee of outstanding scientists reported today that atomic radiation, no matter how small the dose, harms not only the person receiving it, but also all his descendants. So a real focus on the long-term genetic effects. The overall report recommended, among many other measures, reducing the maximum cumulative radiation exposure from 300 to 50 Roentgens and limiting the average exposure through age 30 in the population to 10 Roentgens. Now, both the genetics and the pathology committees addressed the health-related effects of radiation, but they offered strikingly different assessments. The geneticists focused on low-level doses and emphasized that any radiation is genetically undesirable. Even small increases in radiation exposure would result in deleterious mutations or genetic defects, as they put it. And as the report went on to say, each one of these mutants must eventually be extinguished out of the population through tragedy. And so the geneticist's recommendation was to try to keep radiation exposure as low as possible. Now, as John Beatty has shown, it was not easy for the geneticists to reach consensus. 2 of the geneticists on the panel, I suspect it was Muller and Wright, weren't even on speaking terms. And this is why Warren Weaver was brought in to chair the panel. He was not a geneticist. He was an officer at the Rockefeller Foundation with a background in statistics and mathematical physics. But he really worked well to get the geneticists to arrive at consensus for the report. Now, the report from the pathology committee addressed a number of serious health problems associated with radiation exposure, but it was much more reassuring on the issue of low-level radiation. They claimed that radiation under certain levels could be harmless to individuals, and in discussing the late effects of radiation, namely leukemia, among Japanese atom bomb survivors and also radiologists, they insisted that these individuals had received a nearly single fatal dose of radiation, or for those exposed occupationally, higher than acceptable permissible dose rates. So the implication was that exposure below the permissible dose rates would not result in any of these long-term effects, such as leukemia or shortening of life. Now, a 1957 paper by Edward Lewis bolstered the case of the geneticists. He compared studies of leukemia incidence in 4 exposed populations: Japanese atom bomb survivors, patients irradiated for a condition called ankylosing spondylitis, children who were irradiated as infants for thymic enlargement, and radiologists. The risk of leukemia caused by the various kinds of exposure was comparable, leading him to calculate a minimum estimate of induced leukemia as 2 × 10⁻⁶ per individual per rem per year. Now, Lewis argued that this could be attributed to the somatic mutation hypothesis for carcinogenesis, and especially that the linear dose response would suggest a mutation-like event. Based on his analysis, Lewis argued that the growing concentration of strontium-90 from fallout could be sufficient to raise the incidence of leukemia in the U.S. by as much as 5 to 10%. Now, there were genuine scientific uncertainties below this calculation, but his insistence on the linear dose-dependent nature of radiological hazard was very influential. A report from the United States Committee on the Effects of Atomic Radiation, published on August 10, 1958, predicted a rise in additional deaths from leukemia worldwide due to radioactive fallout, just as Lewis had. The increase in radioactivity, they pointed out, was slight, only about 5% of the total radiation received from natural sources. However, even such a small increase in radiation could still lead to measurable increases in cancer. Strikingly, the Baer Committee on Pathological Effects, which was still meeting, issued a commentary on the UN's report. The panel commented, and I'm not going to read you the whole quote, although I'll put it up, but in their quote, they specifically attacked the somatic mutation theory. While somatic mutations may be included among these effects, it seems doubtful that a strict linearity analogous to that seen in the genetics effects of radiation is as likely to hold in the case of these conditions. And they also challenged nonlinearity generally. So the disparity between how the geneticists and the individuals on the pathology committee viewed low-dose radiation is striking, and the fact that they were publishing these reports brought it into public view. Now, clearly part of this reflected disciplinary orientation. It's perhaps not surprising that physicians or health physicists resisted seeing the complexities of radiation-induced cancer reduced to mutations, and there are problems with the somatic mutation theory, especially for diploid organisms. But the 2 panels were also different in the nature and the extensiveness of their relationships to the AEC. The pathological effects panel was populated largely by current and former Manhattan Project and AEC employees. Warren Weaver, who headed the genetics panel through the publication of the 1956 report, actually said that there was a conflict of interest behind the deliberations, as he wrote confidentially to Detlev Bronk in a letter I saw here in the archives. Incidentally and quite confidentially, do you feel entirely comfortable about the degree of commitment and perhaps unconscious loyalty to the AEC that exists in the pathology group? I do not. And in fact, AEC officials and many of its researchers resisted giving up the threshold concept or accepting the somatic mutation theory. A 1958 paper that was published out of Argonne National Laboratory gave the results of a study in which mice were exposed to various doses of strontium-90, and the expected effects of life-shortening and leukemia were seen, but the mice that received the lowest dosage didn't show any of these effects. So the scientist Miriam Finkel argued for a threshold for strontium-90, which was well below the human exposures to fallout. This was then challenged by Linus Pauling and others. And in response to the debate, Argonne's director, Austin Bruce, went on record as asserting that the theory of linearity remained unproven. Nonetheless, the genetic viewpoint eventually prevailed. As the 1972 Baer report stated, by which time it had shifted to being the biological effects of ionizing radiation, until recently, it has been taken for granted that genetic risks from exposure of populations to ionizing radiation near background levels were of much greater import than somatic risks. However, this assumption can no longer be made if the linear non-threshold relationships are accepted as a basis for estimating cancer risks. So in addition, the somatic mutation theory then went on to become, as one book on cancer biology puts it, the prevalent theory of carcinogenesis. So in conclusion, the National Academy of Sciences Baer Committee played a crucial role in this shift, both as a discussion forum for practitioners of the relevant science and as a source of information to both the U.S. government and to the American public at large about the consequences of that knowledge. Now, one might say that I've told this story as a story of triumphalism, of kind of marginalized geneticists seizing the political opportunity provided by the Baer report to get out their perspective on radiation hazard, and this is no doubt true. But that said, the perspective that they had on mutational damage was far from complete. The discovery of DNA repair in the 1960s showed that mutations were not necessarily irreversible for damaging DNA, and the assumption that radiation damage is linearly dose-dependent at very low exposures remained and remains controversial. Members of the biological effects on ionizing radiation were famously unable to reach consensus about the hazards of low-dose radiation exposure in the report that they issued in 1980. Moreover, the shift in the 1970s to analyzing radiation hazards in terms of cost-benefit analysis further complicated efforts to assess what risks were acceptable by rendering a political issue in largely economic terms. And you can really see this in the correspondence behind funding the Baer reports in the 1970s. So the scientific committees appointed by the National Academy of Sciences to address these problems were also not free of entanglement with affected government agencies, and nor could they resolve the most important controversies. But they did bring these controversies to public attention, which itself is an important legacy of the Organization for 20th Century American Science and Politics. Thanks. And there's my book, in case you're interested. So I have a lot more to say in the book about it.
Thank you, Angela. And I will repeat the plug for her book, really masterful study of radioisotopes in the early atomic age. Our next speaker is Kevin Crowley, Senior Board Director of the Nuclear and Radiation Studies Board of the National Research Council, which advises the national academies on the design and conduct of studies on radiation health effects, radioactive waste management, and environmental cleanup, as well as nuclear security and terrorism. Kevin is the principal investigator for the Radiation Effects Research Foundation in Japan, which is the successor to the ABCC from the early days.
Well, good morning, everybody. I'd like to devote my brief time today to a discussion of the science behind some of NAS's contributions to understanding radiation risks in humans. I'm going to describe some scientific concepts and some conclusions that I hope you'll find interesting. Much of the scientific research on radiation effects in humans is being driven by these two questions. What are the effects of ionizing radiation on human health? And what are the biological bases for these effects? These questions have important implications for human well-being, as well as for governmental policies for protecting people from the potential harms arising from radiation exposure. These questions are especially pertinent for exposures to ionizing radiation at doses that people typically encounter in their lives. These exposures are sometimes referred to as low-dose exposures, generally interpreted to mean radiation doses below about 100 millisieverts. I'll try to put this quantity in perspective using this slide. The vertical bar on the slide expresses the magnitude of radiation exposure using a logarithmic scale. The scale is labeled with both millisieverts, which is an SI quantity, and rem, which is still used in US regulations and operations. You can divide by 10 to convert from millisieverts to rem. I'll be using millisieverts throughout this presentation. The low dose interval occupies the bottom part of this bar, below 100 millisieverts. Health effects such as cancer incidence predominate in this interval. These diseases can manifest themselves years and decades after exposure, so they're sometimes referred to as late-term effects. A person in the United States receives on average about 3 millisieverts of natural background radiation each year. So 100 millisieverts represents about 33 years of cumulative exposure to natural background radiation. Health effects at higher doses than low dose include radiation sickness and even death. These effects can occur in hours, days, and weeks after exposure, so they're sometimes referred to as acute effects. Although irradiation at high doses can be fatal, high-dose radiation is also used to treat cancer when it's delivered in a fractionated way. Data on radiation effects in humans were just beginning to emerge at the time that the Baer reports were issued. The most important source of human data on radiation effects is from studies of survivors of the 1945 atomic bombings of Hiroshima and Nagasaki. These studies were begun by the Atomic Bomb Casualty Commission, or ABCC, in 1947, and they're being continued today by the Radiation Effects Research Foundation, or RERF. NAS established ABCC at the request of the U.S. government and has a long-standing cooperative agreement with the U.S. Department of Energy to provide scientific support to RERF, primarily by employing U.S. scientists to work at the foundation. ABCC-RERF has been carrying out long-term studies on 3 survivor cohorts, and those are shown on this slide. The lifespan study is designed to investigate long-term effects of radiation on causes of death and incidence of cancer. This cohort includes about 120,000 residents from Hiroshima and Nagasaki. The in utero exposed cohort was designed to investigate the effects of radiation on fetal development and long-term health. It consists of about 3,600 subjects. And the F1 cohort was designed to investigate genetic effects of radiation on the offspring of survivors. It consists of about 77,000 subjects. And within each of these 3 cohorts, there are ongoing clinical studies shown by the green fields. The ABCC-RERF studies are often referred to as the gold standard for radiation epidemiology studies because they have large size, they've been carried out for many decades, they include both sexes and all ages, the survivors had a wide range of radiation doses, and the studies have a very careful design and execution. Japanese atomic bombing survivors received a wide range of doses from the atomic bombs because of their locations and shielding conditions. This slide shows the distributions of unshielded air doses for the Hiroshima subjects of the lifespan study. You can see that most of the survivors in this cohort were located between about 1 and 3 kilometers from the bomb hypocenter. Relatively few people within a 1 kilometer radius of the bomb survived the blast and radiation. I want to talk about some of the key scientific conclusions from ABCC-RERF in the next few slides. The lifespan study cohort, the results for which are shown here, shows a clear increase in mortality from cancer in the decades following the bombings. Excess deaths from leukemia peaked about 5 years after the bombings. Excess deaths from solid cancers started rising about 10 years after the bombings, and they're still rising. They will likely peak in the next decade. Excess deaths from non-cancer disease, and this is primarily cardiovascular disease and stroke, are also occurring in this cohort, shown by this low green curve here. This peak, the peak in cardiovascular disease is anticipated to occur sometime after the peak in solid cancers. Not shown on this slide, but to date, the F1 cohort, which are the children of survivors, shows no evidence of increased genetic risks. Exposure to ionizing radiation increases the risk for most types of solid cancers. The magnitude of the risks vary by cancer type, and the cancer sites shown in red on this slide have statistically higher risks. Those are cancers of the esophagus, stomach, colon, liver, gallbladder, lung, breast, ovary, and bladder. Cancer risks are also age-dependent. Younger persons are more sensitive to radiation cancer induction than older persons, and their risk persists for a lifetime. Although not shown on this slide, females also have a higher risk than males for some types of cancer, particularly thyroid cancer, lung cancer, and of course, uterine and breast cancer. ABCC-RERF is the most important source of data for radiation health studies carried out by the NAS. These studies, which are requested and funded by the U.S. Environmental Protection Agency, are referred to as the biological effects of ionizing radiation, or BEER studies. Dr. Creager referred to these in her remarks. 7 BEER studies have been carried out to date. The last was published in 2006, and the cover for that is shown here. A key objective of these studies is to develop quantitative estimates of risk for exposure to low levels of ionizing radiation. These risk estimates are used by federal agencies to set radiation protection standards for workers and the general public. I showed this slide at the beginning of my presentation. Here I've removed some detail and I've added the BEER 7 lifetime risk estimates, and these estimates apply to all cancers, and they're shown, they're shown on the right side here. For a single 100 millisievert exposure delivered at a low dose rate, the BEER 7 estimates that risks of developing cancer over a lifetime would increase by about 1%. However, there are sex differences in the risks and there are large uncertainties in the estimates. The risk ranges for 100 millisievert exposure are shown in the red box. You can see it's a fairly wide range and it differs for males and females. I should also note that these estimates are for cancer incidence. Risk for cancer mortality are about 1/2 of these values. Also shown on this slide are two radiation protection guidelines. The 1960 Radiation Protection Guideline, and this was developed based on Baer report findings, established a 5 millisievert annual limit for individual exposures exclusive natural background. Allowable limits have been reduced since 1960 because of the information provided by ABCC and NAS. As an example, the annual limit for individual exposures from nuclear fuel cycle facilities, which include nuclear power, is now about 0.25 millisieverts. This is a 20-fold reduction in the 1960 Radiation Protection Guideline limit. We still have a lot to learn about radiation risks in humans. A key scientific challenge is understanding dose-response relationships below 100 millisieverts, that is, within the low dose zone. The Baer 1 report concluded that the dose-response curve was best described by a straight line that intersected the risk and dose axes at 0, a line like that. This curve is referred to as the linear no threshold, or LNT. BEER 1 selected this curve for pragmatic reasons, not because it was indicated by the available scientific evidence. The BEER 7 report, which is the most recent BEER study, noted that statistical limitations make it difficult to evaluate the shape of the dose-response curve at low doses. Nevertheless, the study concluded, based on a review of the biology, that LNT applied at low doses. The plot shown on this slide is from the BEER 7 report. It shows the risks of solid cancer as a function of dose for the Japanese survivors. The LNT curve, the solid line, the straight solid line, was used to fit this curve, and it described, statistically speaking, it provides the best fit. However, notice that most of the data used to fit this curve are for doses well above 100 millisieverts. The 100 millisievert boundary is right there, and the low dose range is the area between the dotted lines. Further progress in understanding risks at low doses will likely come from research in radiation biology. To date, this research has uncovered a number of mechanisms for cell and tissue response to ionizing radiation. However, the elucidation of a biological model for radiation responses in complex living organisms remains a key scientific challenge. Thank you.
Thank you, Kevin. Our next speaker is John Garrick. John is a member of the National Academy of Engineering and Vice Chair of the National Research Council's Committee for Improving Safety and Security of U.S. Nuclear Plants. He served for 10 years on the Nuclear Regulatory Commission's Advisory Committee on Nuclear Waste, and he chaired the National Academy of Engineers Committee on Combating Terrorism. And from 2004 to 2012, he was chair of the U.S. Nuclear Waste Technical Review Board, a presidentially appointed board. Welcome, John.
Thank you. Thank you. Good morning. Doctors Creager and Crowley have very interestingly chronicled the events and debates shaping our understanding of the acute and latent biological effects of radiation. The separation of somatic and genetic linkage have occupied much of the debate, on this topic, especially during the 1940s and the 1950s, and the institutional problems and issues that Dr. Creager indicated were most fascinating part of the story. My interest in radiation hazards is from the point of view of quantifying the risks, both safety and environmental, of activities involving very large inventories of radioactive material. The nuclear power plants are the primary example. The focus of the nuclear plant risk studies is on high consequence events, such as severe accidents that might occur from within the facility or as a result of an severe outside event, such as a severe weather event, or something of the magnitude of the great Eastern Japan earthquake that occurred on March 11, 2011. The credibility of quantitative risk assessment depends primarily on two factors: the ability to model events that lead to radiation exposure threats, that's a big one, and the ability to represent the health and safety effects resulting from the exposure, the subject of this panel. Consider the effects on the screen. These are bottom line results of one of many industry-sponsored full-scope risk assessments that I had the honor to lead, and this one was over 30 years ago. This study followed the publishing of the reactor safety study for by the U.S. Nuclear Regulatory Commission before the Nuclear Regulatory Commission had any policies, regulations, or rules on risk assessment. Such plant-specific full-scope assessments have not been performed since the 1980s. To be sure, there have been risk assessments, but they've been limited in scope. The figures illustrate 6 measures of risk: early fatalities, injuries, thyroid cancers, latent cancer fatalities, whole body dose, and property damage and evacuation costs. And this particular analysis is based on the health effects model of the 1972 Beer report. The risk curves are presented in the form of frequency as a function of consequence, with probability as the parameter of the model represented by a family of curves. The question relevant to the topic of this panel is, where are we now with respect to modeling health effects, and how should our current state of knowledge impact our attempts at quantifying the risk of complex nuclear systems? For some of the answers, I turn to the Beer 7 report. The advances certainly continue the trend noted by Dr. Creager in her remarks and have to do with, among other topics, a better understanding of the relationship between spontaneous mutations and naturally occurring genetic diseases. One of the important conclusions, as we've already heard in the Beer 7 report, and similar to previous reports, was, quote, the linear no-threshold model, LNT, provided the most reasonable description of the relation between low-dose exposure to ionizing radiation and the incidence of solid cancers that are introduced by ionizing radiation, end of quote. So what does this mean to the risk analyst, like me, attempting to perform quantitative risk assessments of models of complex systems, where by quantitative, what I really mean is quantification of the uncertainties in the risk measures? Well, consistent with consistency in terms of the rules of the engagement of probabilistic type risk assessments would suggest integrating or fusing the various dose response hypotheses probabilistically, of course based on their credibility, to evolve an evidence-based model, avoiding the need to choose one over the other. That way, the evidence supporting linear and nonlinear, threshold and non-threshold hypotheses is represented in the dose response model based on scientific principles. Included in the fusion process would be such dose response hypotheses, of course, as LNT, threshold models, and hormesis models. Such an approach would seem appropriate, especially given that the Beer report notes that there are still significant uncertainties about the mechanisms that lead to adverse health effects following exposure to ionizing radiation. especially with respect to low levels of radiation. Basing our risk assessments on just one of several hypotheses is not quite in keeping with the spirit of quantifying the risk. So, what other changes might be in order for our risk assessments, and how might they impact the curves I showed you? For example, what new evidence might lead to higher estimates of risk than estimated in the past, and that's represented by these curves? Well, certainly one is non-cancer health impacts, such as radiation-induced chromosomal aberrations that could lead to adverse health effects for some population groups. Neurological damage is another health effect that I am told that has a very different biology than cancer. Another that is frequently mentioned is the psychological consequences of being exposed to low doses of radiation, a factor that could be important in formulating nuclear plant evacuation strategies. It has been observed, as a matter of fact, that stress-related phenomena in the aftermath of Fukushima, some due to extended evacuation and relocation, may have resulted in a significant number of deaths. The point being that basing too much on a single hypothesis without due consideration to others could lead to making the wrong decisions. What about changes in our state of knowledge that could lead to lower estimates of nuclear facility risk from what we'd calculated 30 years ago? Probably the biggest impact on reducing our estimates of nuclear power plant risk has very little to do with the health effects model, and that is what we have learned from the accidents about the releases following a reactor core meltdown. In particular, the evidence from the accidents that have occurred indicates far more confinement capability of the radioactive material during the progression of the accident, even in the presence of degraded containments, than we took credit for in our earlier risk assessments. Of course, the next accident could be a different story, and we have to account for that in our probabilities. But for the 4 light water nuclear power plants that have melted their cores, TMI and the 3 in Japan, there have not been acute radiological consequences, which to the nuclear facility risk professional is a major and positive surprise. To be sure, we have yet to determine what the latent effects might be. So, how would the curves I presented change, and in what direction as a result of the advances that have been made? Well, I don't really know without having done the assessment. But my judgment is, had we known then what we know now, the uncertainty spread would be somewhat less than shown in these curves. But I suspect that the central tendency parameters would not change much because of offsetting effects. A final comment I would like to make has to do with what I believe is the value of a probabilistic framework for considering issues where different hypotheses or theories are involved, each having its own uncertainties and supporting evidence. A probabilistic framework can be an effective approach for providing resolution between what we know a lot about, what we know a little about, and what we don't know, and the various states of knowledge in between. Quantifying the uncertainties probabilistically greatly facilitates the calibration of states of knowledge of fundamental processes, such as the biological effects of low-level radiation. It allows for a systematic process to integrate and fuse all the hypotheses considered into a representative model without having to choose one over the other. Let the totality of the evidence determine the dose-response model. The Beer studies have been enormously beneficial in providing reference material on the state of the relationship between exposure to ionizing radiation and human health. In my opinion, the information would even be more valuable, much more valuable, had the Beer Committee adopted a probabilistic framework to process their findings and more quantitatively presented all the supporting evidence that they considered. As a believer in the quantitative approach to risk assessment, let me just end my remarks by observing that the goal of the risk sciences should not be to just bound the results or necessarily to even seek conservative results. We all know that if we keep pushing the conservative button, there comes a point when we are no longer conservative, we are simply wrong. We can do much better than bound our results using the uncertainty sciences. The goal of the risk scientist should be to present the truth about the results, which means quantifying the uncertainties and making transparent the supporting evidence and our confidence in the results we develop. Thank you very much.
Thank you, John. Our next speaker is Susan Lindee, the Janice and Julian Burrs Professor of History and Sociology of Science and Associate Dean for the Social Sciences at the University of Pennsylvania. Her research interests include American science, history of genetics, gender and science, science and popular culture, and science and war. And in addition to her very thought-provoking history of the Atomic Bomb Casualty Commission, she is author of Moments of Truth in Genetic Medicine, and the chapter Censoring Science in Evan Gerstmann and Matthew Streb's edited volume on academic freedom at the dawn of a new century, How Terrorism, Governments, and Culture Wars Affect Free Speech. Susan.
Thank you, Peter. I'm just going to stay seated because I don't have a PowerPoint. And what I hope to do is open up some frames for discussion, more like what are some theoretical perspectives or what are some broader ways of thinking about the really fascinating questions that our panelists have raised, historical, contemporary, and I think in John's case, methodological. What do you include when you undertake to study something as high risk and complicated as radiation exposure of many different kinds of populations under drastically different circumstances and with drastically different I would say something like cost-benefit calculations, because you have medical patients and you have worker exposure and you have persons exposed in accidents, and there are a lot of different ways to be exposed to radiation at levels that are vexing that we need to address. One of the things, John, I did a lot of work on the Atomic Bomb Casualty Commission, the history of its creation and the early struggles to figure out how to manage dosimetry, how to decide what counted as a mutation, how to see heredity when you looked at these populations, and also how to navigate the complicated social world of post-war Japan. Remember, most of those who were running the ABCC in the early years were American geneticists, American physicians, and they depended on powerful relationships with Japanese physicians and also with the Japanese community. So that's part of what I was interested in at the time. But one of the things that struck me is that the Atomic Bomb Casualty Commission never included attention to psychological, social effects or to the consequences for a society that so many of its members were, first of all, killed, that you annihilated all the infrastructure, and also that there were such long-term potential biomedical consequences of exposure to radiation. And it really wasn't until Robert J. Lifton in the 1960s began to interview the survivors that there was even an effort on the part of American scientists to try to understand the psychosocial dimensions of the bombings. And remember, one of the key justifications for studying the survivors at Hiroshima and Nagasaki was to provide insight to American planners for civil defense. That is, what did we need, how did we need to prepare American populations for what was expected to be, in all likelihood, a future nuclear war. It's pretty scary to reconstruct or to read seriously how nuclear theorists thought about the likelihood of nuclear war in the 1950s. They generally expected it to happen, and it was our business to prepare. And that kind of climate, and I'm going to refer to this again later. I want to call that something like anger and fear, because I'm going to refer to emotion again. So the anger and fear in nuclear strategy circles, and how that shaped the decisions they made about these studies of the biological effects of radiation. Now I have three bigger points, and the first is that the National Academy of Sciences has played a major role not only in studying in participating in these studies of the biological effects of radiation, but in an ancillary sense in the development of human genetics. And it's common now for historians to say that human genetics got its big bump from the bomb. The bomb was the best thing that ever happened to human genetics because it led to important sources of funding, it led to significant government support for human genetics research, it justified major field studies. You may be familiar with all the field studies of isolated populations in the 1950s and 1960s. Those populations were presumed to be pure and therefore a source of data. They were unexposed to radiation, and they were therefore a source of data on what the normal mutation rate was in human populations. And in addition, support from the Atomic Energy Commission, which really, you can't find a prominent geneticist in this period who was not supported by the Atomic Energy Commission. You can't find an important environmental scientist who was not supported by the Atomic Energy Commission. And the notion that, and Angela sort of referenced it, but the notion that Atomic Energy Commission funding somehow led to a given conclusion about radiation risk is really, it's not so clear. I mean, H.J. Muller was getting a lot of money for about a 15-year period from the Atomic Energy Commission, even as the AEC was attacking him publicly and was pretty much ready to strangle him. And so the question of what impact does AEC funding, and I know personally from, working, I mean, most of James Neal's research was funded by the Atomic Energy Commission, but there is no, if you read his efforts to make sense of what he was seeing, of the biological data, he was clearly engaged in an epic and very serious effort to accurately assess what he had seen. And so it's not like there's no undercurrent of the AEC wants me to say this. And he had a very strict sense of a firewall between the results and the Atomic Energy Commission. So I mentioned human genetics, and I just want to, we might say that genomics arises out of this question of the genetic effects of radiation. It becomes possible. Remember, the first proposal, the first IBM conference on mapping genes was 1959. So the notion that you could map genes based on computing was there very early, and Victor McKusick was suggesting the mapping the human genome in the 1960s. My second kind of broader point is about, I want to mention the risk society, and this is a concept from Ulrich Beck, and I want to suggest that radiation studies perfectly exemplify what he was referring to, and this is that what he proposed is that we have become a society in which risk and uncertainty are the fundamental organizing principles, and in which we study with scientific tools risks which are created by scientific discovery. So you discover the possibility of nuclear weapons and of nuclear energy. This creates risks which then can be assessed through a different suite of sciences and a different kind of technical knowledge. And it's this sense of a risk society where the risks involve uncertainty. Technoscience is an exemplary domain of kind of the organization of our society, where there's a very strict and interesting cost-benefit calculus that the scientists are asked to conduct, and where there are many different kinds of scientific experts involved. And what I wrote here too is that the effects of these risks are also lumpy in distribution. That is, some people are at high risk and some people are not. So how does social organization shape who is at risk? I want to suggest that when we think about the NIS's contribution, it's not so much the victories or the failures, but we ought to have some respect for the process that's carried out with integrity, or that intends to have integrity. And this is the messy process that Dan was talking about yesterday. It's this process of multiple voices, conflicting voices, lumpy consequences, uncertainty, risks at multiple levels, and data that don't exactly speak in a crystal clear voice. And that's definitely certain for the radiation data. Finally, I want to bring up something that no one else brought up, but that I heard in the talks, and that's something like interests and emotions. Neal, Muller, and their peers were really struggling to understand these risks, and it was common for those who argued that radiation was a higher risk than it seemed to be called emotional. So John Goffman was called an opera star by one of the AEC commissioners. Mueller was commonly called hysterical or overly emotional. I noticed that he was called a sister in Angela's talk. So it's almost as though being overly concerned about radiation risk was somehow over-emotional, was even feminine. Harold Knapp, who wrote a paper challenging AEC standards, I think this was in about 1963, was accused of being emotional, and Knapp actually worked for the AEC. So different people, those worried about radiation were emotional or even feminine. But in retrospect, if we think about the perspectives of the hardcore Cold Warriors, there was a certain amount of emotion involved in their decisions about how many bombs were needed. I don't know if you've ever read Atomic Audit, but it's a pretty depressing story about how much money was spent on nuclear weapons and why those funds were distributed in that way. And it was partly a sense that the risks were incredibly high, and maybe they were. But the important point I'm trying to make is that emotion is present on all sides of this debate. There's no way out of it. And this has to do with whatever we think about conflict of interest, whatever we think about neutrality or purity or the autonomy of science. And so I'll close by saying, as we stand now, what sense can we make of neutrality, disinterestedness? These are ideas which remain important and appealing in the scientific community. They matter to all of us. You don't work on the history of science if you don't think that science is one of the most important human endeavors that we can imagine, if you don't have a stake in its quality and its success. But also, today, scientists face complexities, and maybe we need a new vocabulary regarding emotion, disinterested, neutrality. What does it mean? You know, we were talking about the interest that different parties bring to the table when they come together to reach these conclusions about science. And even on the panel today, there are different perspectives. How do we think about that? How do we come up perhaps with this new language or new vocabulary regarding emotion? And then finally, I guess one thing that this overall project could do is help us think about how the history of the National Academy of Sciences, which is really to a remarkable degree always in the middle of the very messiest aspects of 20th century science, how can this help us imagine its most productive future role?
Thank you, Susan. So now I think we will have some time for the panelists to respond to each other's comments. If anybody has anything they'd like to say off the top of their heads or questions to pose to the others. John?
I'll start it, since I'm often the controversial member of the group. I wanted to ask Kevin about this problem that I see in National Academy and National Research Council committees, and I've served on a whole bunch of them, and particularly on issues like this. It seems to me that one of the requirements for really understanding these kind of issues is making sure that people that are involved in developing the work include people that actually use it in the sense of broad application. And I know how difficult it's been in some of the NRC committees to staff the committees in a way that, at least at the outset, without having to do it by bringing people in to represent the technologies that the committee is actually trying to address. And has that been a factor in the Beer reports? How many people that actually use the output of the Beer report in doing major calculations? These risk assessments are multi-million-dollar efforts, and there's tremendous investment involved in them. And I sometimes don't get the sense that the people that have to use the material are as well represented in the development of the basic information as they should be. Can you comment on that?
Well, that's a good point, John. I think with respect to the Beer studies, if you look at the composition of the committees, they've been very heavily scientific in the disciplines that are really focused on what happens at the cellular level, and also people who know how to do epidemiological studies and statistical experts. I can say that on other studies that we have, and a good example is a study that you're serving on now and that I'm directing on the lessons learned from the Fukushima nuclear accident. An issue there is that we were asked by Congress to look at what happened at Fukushima and then to give advice to the U.S., both to the Nuclear Regulatory Commission and the nuclear industry. And of course, to understand what happened at Fukushima, you'd like to have people on the committee who understand how nuclear plants operate and maybe who have had some experience in those operations. The problem is that there's a conflict of interest issue. And so there is this tension whenever we do a study about making sure that you have all of the perspectives at the table, and I think the user perspective is a very important perspective, but doing it in a way that doesn't discredit the study because the committee either has or is perceived to have strong conflicts of interest. I would make one other comment that with Beer 7, I think there was a recognition about how controversial this was and how strong the different viewpoints are, the linear viewpoint versus the hormesis viewpoint. And the way that the Academy tried to deal with that was to bring in some prominent scientists who didn't work in this field to sort of be the neutral parties that could sort of stand above everything and evaluate the evidence and to make sure that the committee really gave all of the issues a fair hearing.
Just to expand on that a little bit, it seems like this subject is one which is a little bit like climate change in the sense that you have this series of panels, and the Academy is grappling with this problem now for 50 years. And you have, bear and then beer, and you have this series of beer panels, and similar with climate change, the Academy has grappled with this periodically. And, why do we need this series of reports, these iterations? And is it because the problem has changed, or is it because the science has changed, or is it because the audience has changed over time? And in this one, I'm curious about this question of the audience for this, or I think Elliot's question yesterday was about who are the users, or who's the audience. In this case, we're talking, is it the policy people, or is it the policymakers, and has that changed from, say, the AEC to the EPA, which is, I think, a different audience, or is it the reactor designers, is it the epidemiologists, public health, medical professionals, scientists, or the developers of these statistical models? What do you think of as the users or the actual audience, and then how has that audience maybe changed over time?
Let me take a start at that. Speaking specifically to the beer studies, I think the reason that there have been multiple studies over time is because the data have changed. And in particular, the data from ABCC RARF. The events that have driven new beer studies are, number one, the dosimetry of the atomic bombing survivors have been redone twice, the first in '86. That prompted the 90 report, and then in 2002, the dosimetry changed again, and then we had the Beer 7 report in 2006. And then every 7 to 10 years, RARF updates these very large studies. They publish an update of the lifespan study, for example. They do an F1 study. So those are the main drivers. And then I have to say, over the past 10 years, there's been a lot of new research on radiation biology. Right now, our understanding is basically epidemiology, and now we're getting to the point where we're beginning to have a mechanistic understanding that can help us interpret the epidemiology, and I suspect that that is what will drive the next beer study. The end user for beer is very clearly, it's been the Environmental Protection Agency and other radiation protection agencies around the world. And they are more of the followers rather than the leaders. They see that the science is changing. They ask us for an assessment. We do an assessment, and then they take that assessment, and then they, if warranted, they then will change their regulations and their standards.
I think it's important to understand that one of the interests that has been challenged by the Bear reports is actually the medical profession and the medical supply industry. And interestingly, the strongest reactions against the first Bear report that I saw in the archives were from the Picker X-ray company, which was very concerned that there's very strong recommendations about lowering doses and clinical uses of radiation would affect the willingness of radiologists to use X-ray machines. And I mean, this is a very complex issue. I mean, the kind of benefits versus the risks of medical uses of radiation. But we often think about the nuclear power industry as the main source of artificial radioactivity that people are exposed to, but medical uses, as the Beer reports point out, is a much larger source. And when we think about kind of the values of that, I mean, people are much less hesitant to expose themselves to radiation if they have concerns about their health than if they think about power plants. But it remains, you know, a live issue whether the level of radiation exposure we get through dental X-rays and especially now CAT scans, which really use a lot of radiation, whether that's warranted or whether it's worth the additional risks.
I'd like to ask the historians, the experts on this business of making records and telling it the story of how things happen. How do you keep the process balanced? You know, in my lifetime, when I was very young, Columbus was a hero, and now he's viewed as a proliferating, greedy frontman in the interest of wealth. And so what are the means by which the history can be told about this and with some degree of assurance that it's balanced? How do you do that?
It depends on what you mean by balance, and I'll just briefly address that. What you're usually trying to do when you tell a historical story is to figure out a way to tell the story that is informative or illuminating regarding larger processes. So it's not heroes and villains necessarily. It's how do the experiences of these people help you understand something about something else, maybe the nature of democracy, maybe the nature of class, social class, how gender works, or in the case of science, something like how knowledge works in social systems. And so it's not so much, I mean, your example of Columbus is not quite what we would take as the key example. It's not heroes and villains, it's rather what is the integrity of the story you tell? Have you done your best to collect as much information as you can, and is your focus right? Have you swerved it the right way?
Issue, and it's one that I struggled with when I was writing my book on radioisotopes, especially in addressing the issue of radiation hazards, which are present and were definitely underplayed in the early years of the AEC, but also just kind of the value of these new scientific tools. I mean, I didn't kind of say this explicitly, but the whole radioisotope distribution program relies on the assumption that very low-level exposures are okay. And they can be managed safely. And as the fallout debate proceeded, it called that assumption into question. Now, in fact, the use of radioisotopes was tremendously powerful in science, and part of what I try to show in the book is that part of the legacy of the bomb are all of these advances that came out of radioisotopes that were being made in reactors and distributed in the name of civilian uses of atomic energy. Now, you know, was that worth the occasional risks or whatever, you know, low-level risk? I mean, that's a question that historians can't really adjudicate, but what we can do is to try to show the interests of various parties involved, and sometimes the unanticipated benefits as well as the risks of these new technologies. And, you know, in the end, I don't know, I'm sure some people will see my book as being too apologetic for the AEC, and other people will see me as being much too harsh on the AEC. But part of what I try to show is even within this government agency, there were really different views about how this should be used, what justified it, but there did tend to be a shared assumption that the civilian development of atomic energy should happen, and that whatever risks existed would probably be more than balanced out by the benefits. I mean, we now might call that assumption into question, but it is assumption that really guided government policy for a long time.
I'm not sure that what we're doing is so different maybe from what the Academy tries to do in accounting for many different points of view and accounting for complexity and then trying to assemble some kind of coherent analysis and conclusions out of that. But I think that might be a good way to segue to accepting some audience from the questions from the audience, since we have some time and we have some people already queuing up. So let us start with, is that Naomi?
Hi. This is a quick question for Dr. Garrick. Dr. Garrick, you talked about incorporating the hormesis hypothesis into probabilistic risk assessment. So I was wondering if you could give us a little update on what the scientific status of evidence for hormesis might be. And then if you could say a few words about how you think about quantifying the inclusion of a hypothesis that is a minority view but might yet still be worth considering. So how do you do that quantitatively?
Well, on the latter one, my model for that is not unlike the contemporary thinking about how you do expert elicitation. As many of you realize, I'm sure, that in this world of rare event phenomena, to do risk assessment, you have to depend quite extensively on expert elicitation. And the processes that have evolved have improved that as a source of information a great deal. And I think that in that is some of the ideas that if I were to try to write a paper on how to do it, I would probably start with some of those principles. For example, I would try to establish the credibility of the different hypotheses, and I'm sure I'd screen some of them out. And then I would try to on the basis of the supporting evidence, establish maybe in something a form as simple as a histogram, the credibility of the hypotheses that survived the screening. And then that would then take me to the next point where I have a basis for how I might want to weight, if you wish, the various dose-response curves. So there's very number of ways it could be done, and I'm sure the way that would make the most sense would be far more sophisticated than that. As far as the hormesis, what I looked at primarily was the various studies that are outlined even in Beer 7, and all of these hypotheses are discussed there, and the Beer Committee heard from representatives from each of the parties. But I also was quite impressed with the French Academy and the work that they have done, and the work and their concept of the behavior of the dose response at low levels, including hormesis. So I looked at the same documents that are referenced in the Beer 7 report, and my argument isn't that they weren't considered. My argument is simply that in processing the information, in my view at least, I think they could have better represented the evidence that exists than by just choosing one.
Dick.
Thanks for these very illuminating talks. But I wanted to make sure that Kevin Crowley had a chance to say precisely what he meant. He had a slide in which on the right there was 1% probability of cancer, and he said it was increased by 1% lifetime probability. But that's an absolute increase, not a relative increase. And so your chance of having cancer or a lethal cancer is half that. Is increased by 1%, absolutely. It goes from 20% to 22%. That what you mean? Not from 20% to 20.2%.
Well, yeah, that was actually, Dick, that is for incidence, not for mortality. So
right.
On average, about 42 out of 100 people will develop cancer, so it would go from 42 to 43. And about for every one of those cancers that, new cancers that happened, about, at least based on current statistics, about a half a person would die.
Right, thank you.
Yeah.
I want to thank you all for an incredibly stimulating presentation from everyone. I'm sorry. Can you hear me now? Okay. I want to thank you all for an incredibly stimulating morning. I have many questions. I'll only ask one, but I just want to make a quick comment as an historian in response to your question about balance. I prefer to think about balance in a different way, which is that especially when doing the history of science, to explain to the public that nothing important happens for just one reason, and that life is complicated, science is complicated, public policy is complicated. There are no heroes and there are no villains, but there is complication. So that said, the question I'm going to end up asking, because I think everyone might be able to participate in answering it, is an historical question. It has often seemed to me that the anti-science movements of the late 60s and 70s, which play such an important role in the history of science in the United States as well as elsewhere, started in the 50s and 60s with the fallout controversy. Does that seem right to you?
For environmental concerns, it very much seems right. It's not incidental that Rachel Carson's Silent Spring starts with referring to radioactive fallout and then to chemicals as kind of the lesser known and sinister companion to radioactive contamination. And I think also the reaction of the AEC and especially Lewis Strauss to public concerns in the 1950s definitely helped to generate public distrust of government officials around safety issues around radiation. So I think there were some key moments, and also the AEC lost a lot of credibility in how they were handling siting issues and issuing of licenses for nuclear power plants in the late 1950s, the late 1960s and 70s. So I do think that the arena of radiation hazards was very important in terms of those social movements and the kind of distrust of authority that fostered them.
I'd like to add, I agree with Angela, but I think it's also important to recognize that many of the key actors in criticizing science were scientists. And it comes out of activist scientists, activist physicists and chemists in the 1950s who begin to question the practices of their fields and begin to raise red flags about the social consequences of science. And I would even say not only are they first, they're the leaders. And when you start to look at who is actually generating, who joins these groups, maybe it's Quaker scientists, maybe it's physicists who become burned out. The most vociferous critic, one of the most vociferous critics I've found of science in about 1960 is a physicist who became a sociologist because he wanted to study how pathological the physics community was. So how do you move? You move from expertise to a different kind of expertise that permits you to, and he wrote a series of incredibly nasty papers about how awful scientists were.
I think it's also important when you talk about the AEC history in the 45 to 50 plus time frame to recognize that when the Atomic Energy Act of 1954 was implemented, it was implemented to open up the nuclear world for the development of civilian applications. But it also it contained all of the elements of the discipline, that is to say the promotional elements as well as the regulatory elements. And I think sometimes you have to sort that out in order to fully appreciate some of the positions that Angela discussed. It was a very exciting time. The first big conference I ever attended was the 1958 conference in Geneva on the peaceful uses of the atom. There's never been a more exciting event in terms of the progress of the human species than what I saw at that meeting, that nuclear was going to solve all of our problems, medicine, energy, everything. And so, and I'm sure there was a spin-off from that level of enthusiasm that tainted the objective positions of some members of the community. But I think it's important from a historical standpoint to appreciate the boundary conditions that existed at that time. And it's taken a while to sober up, if you wish, and realize the constraints that existed and the risks that are involved. And I think that has happened, and for the most part, very constructively.
I'll have several questions over here, please.
Thank you for your comments this morning. I was struck first by the desire of these researchers to have a control group for the radiation studies that they were investigating, sort of these isolated populations. And I also surmise that sex differences were clearly investigated because of the fetal consequences. But I'm also curious about how other types of bodies were described and constituted by these NAS reports and NRC reports. And by other bodies, I mean black bodies, brown bodies, Asian bodies, or perhaps if this is drawn along national lines, Japanese bodies versus American bodies. So that's my first question, is how were other types of bodies described in these reports? And also, the second part to this is, were the NAS reports and BEIR reports concerned with exploring how radiation affected these different bodies, and because of that sort of reified these differences between human groups?
I can actually address that a little bit, because you're asking partly about the history of biological anthropology and the roles of geneticists in field research with biological anthropologists, which really escalated in the 1950s and 1960s. And there's no simple answer to your first question, that is, how do different groups look when you reach conclusions about the risks of radiation? Remember that when James Neal went to work with the Yanomami, he believed he was looking back in time at the human ancestors, that he was looking back in human evolution. These were people in the 20th century, and he thought he was looking at the past. So, and by looking at this past, he was going to illuminate all the potential futures and risks and so on. And that would be a common way of seeing isolated groups around the world. Is it implicated in ideas about racial difference? Absolutely, because they were believed to be genetically different and genetically identifiable. And so their genes would illuminate race on multiple levels. And remember, many of the early biological anthropologists had a pretty strict conception of what the races were like and what they did. So yeah, it's a part of this story, but it's so complicated, and it's never just about radiation. When you go when you're studying these isolated groups, it's diet, it's practice, it's kinship, it's taking their hair and their blood, and I mean, Neal was collecting everything, every sort of bodily material to characterize the very different groups. So.
Are almost out of time, but we have 2 people left. I'd like to make sure that we get all the questions, so why don't we if we can take both questions at once to make sure we get Maxine as well, we get both questions on the table, and then the panel can respond, if that's okay.
Hi, good morning. Thanks for a very stimulating panel, as everyone said. My question or comment and question has to do with what I heard yesterday, what I'm hearing today, and and the emotion. This is emotional. I mean, to say scientists aren't emotional or engineers aren't emotional is too naive. I think we all know that. The idea, as Dr. Garrick said, you can't divorce the use of the bomb and the bomb scientists. From what I know of the history of the Manhattan Project scientists, there was a lot of remorse. It wasn't a clear call to use the bomb on people. And that has to shadow everything that happened since, in my opinion. And then the Peaceful Uses Initiative, Eisenhower's speech at the UN that put us on this trajectory and put us here today to talk about this subject, I think is all connected. My question, tying to yesterday, is we're looking at this in some isolation. I want to put context and perspective in the conversation. Yesterday we were talking about the environment, CO2. And today we're talking about one of the big applications, not just medical, but is electricity and energy. So how do you, and what's the role of putting these risks, granted we want to understand them, down to the 0-0 axis that you gave us, Dr. Crowley. How do you put that in the context of air pollution and other uses, this risk-benefit? How do you be pragmatic with the science? The other piece from yesterday was about communication. You show your results in log, 10, 10, 10, 10, 10, but the linear one was linear. And way down there, 0, was where this whole business of what we're really low level is talking about has one data point. How do we communicate that?
Okay, why don't we get the question from Maxine and then let the panel respond.
So my questions are quite different. One question I have, actually both questions have a historical sense in that I think it's really essential when we think about these things to understand how both the world and in particular the relevant science has changed in the years since all of this was going on. If you think about the first Beer Committee, we had just learned that DNA was a double helix. We didn't know about the genetic code. We didn't know about the chemistry of DNA damage. And with each Beer report, it's important to realize that each was written in an era when the science was changing rapidly, and you needed to account for that as you went along. And one of my examples for that would be that the reason why Ed Lewis did that study on leukemia, which Professor Creager mentioned, was because he was a fly geneticist. And he had used radiation to produce mutants, and he understood that. In fact, he sent vials of flies to Bikini to be exposed, and then looked at mutations. So I think you're all historians, but I think the history of the progress of the science really has to enter into any evaluation we make of what the NRC has done. Another thing I found missing, particularly in the discussion of the first Beer report, was the political climate. You guys talked about Mueller, but nobody mentioned that Mueller was under suspicion of being a communist, and that certainly colored the response to anything that had Mueller's name on it. So I wonder if you'd comment on that too. Thanks.
Mueller was a communist, so that's not, it wasn't, I mean, he was very sympathetic to the communist cause.
First of all, I think these are really good points, and actually in a longer version of this paper, I do address the fact that by the 1960s, the fact that, people were understanding DNA to be the hereditary material helped to make sense of the somatic mutation hypothesis in ways that weren't so clear, even at the time that Lewis did his study. Although the double helical structure had been proposed, it took several years for people to really accept it and also to begin to shift their thinking to nucleic acids being the object that was being damaged by ionizing radiation. And obviously the discovery of thymine dimers and other forms of DNA damage was really instrumental. The other reason that shift in science was so important is that people could begin to think about chemical carcinogens as having similar effects to radiation. So having DNA as the locus not only brought together genetic and somatic effects, but also helped to make sense of a broader repertoire of carcinogens and how they might be inducing cancer. So, and certainly you're absolutely right to point to the heightened political anxieties around anti-communism, which certainly were behind Louis Strauss's viewpoints. And Mueller too, although he was always talking about how potentially hazardous it was, that with the atomic weapons testing and medical uses of radiation would lead to more mutations, and he had a much more dire understanding of the effects of those mutations in the population than some other population geneticists did. He also argued that basically weapons testing was justified because of the potential aggression of the Soviet Union. He just wanted the cost to be clear to the public. So, and I think that brings us to this issue of how politics plays into perceptions of costs and benefits. And I think the thing I would want to say to the first gentleman that asked this question is that science and technological expertise play a really important role in helping us to understand what the costs are and what some of the benefits are, but ultimately we can't ask science to adjudicate what are political questions. And this is where we're back to the messy democracy that Dan Kevles referred to in his opening comments.
Just quickly, two other comments to address the first question. As satisfying as it would be to scientists to be able to put all of the different technologies like energy technologies on the table and do a systematic risk, that ain't the way it works. We do this in a piecewise fashion, and society, through our political process, decides what's an acceptable risk. In terms of that low dose region and the one data point, this is a limitation that you have with epidemiology studies. The epidemiology studies will get you to the top of that low dose zone. There are actually some very interesting epidemiology studies now involving medical radiation that is sort of inching down toward the center of that zone. There was a recent study on CT scanning in children from the UK that showed an effect pretty similar to what would be estimated for atomic bombing survivors, down to about 60 millisieverts. But I think if you really want to understand what's going on down in the zone, particularly down in the lower part, we're going to have to do a better job on the radiation biology.
Okay, I think I will thank our panel, and I will also add that both John and Maxine mentioned the need for historians to try to get in the heads of the people they study and be able to transport yourself back to the 1950s in that context. And I would mention that there's a marvelous time machine right here in the Academy's building. It is the archives upstairs. And you can go up there and pull out some folders from this period and find yourself magically transported back to whatever time you're looking at. We will reconvene in about 15 minutes after the break.